Good.
Okay, I will introduce you briefly. So good
Thank you,
afternoon.
Prof.
Let me check. Yeah, we are recording. Good afternoon, everyone. Welcome to this edition of the NITheCS mini school. My name is Francesco Petruccione. I'm the director of NITheCS, and I'm based in Stellenbosch. And today, it's a really great pleasure to introduce to you Dr. Farai Mlambo. Farai is at the Wits Business School, where he's a senior lecturer in digital business and data analytics. He also involved as a research fellow at the relatively new Wits Machine Intelligence and Neural Discovery Institute, also called MIND. Yeah, so that's really very nice. And most importantly, he's a NITheCS associate in the discipline of statistics. That's the most important thing to us. Yeah, and very soon he will also give us a NITheCS colloquium in a couple of weeks' time, I think. Yeah, on a book that he wrote. Yeah, a survival guide for every postgraduate journey. Yeah, and please don't miss that. That will be very important, and not only for the postgraduate students. Yeah, also some of the older supervisors can learn some tricks there. Yeah, so. Farai, without further ado, now we've hit almost 120 participants. Thank you very much for offering this very exciting mini school in November. And please, over to you.
Thank you, Prof. I really appreciate and I appreciate the fact that there's quite a number of people here coming in, and I don't think they came because of my title, Prof, but I think they really wanted to hear you as well today.
No,
With
they're here for you. They're here for you.
awesome introduction. So thank you so much, everyone that could make it this afternoon. So I'm just going to start sharing my screen, and then we can get into some business. So give me a second. I just need to make sure that I share the right screen. Okay. So, okay, just give me a second again as I set up one or two things which I need to.
We can see the PDF now. Yeah.
Wonderful. Thank you, Prof. So I just need to move my Zoom chart to a different screen, which I'm done with. Okay, great. You want to see what people are saying as well when you are teaching.
Yeah, no, that's excellent. And but we will, Farai, we will collect all the answers, all the questions, maybe at the end of the talk, so that because we are recording it and we would like it to be in one go. Okay.
In one go. Perfect.
I will keep quiet now, and the participants are welcome to add their questions in the Q&A. Yeah.
Good.
And maybe at the end we can give the other participants also the right to speak and ask questions in person. Excellent.
Good.
Thank you very
Thank
much.
you.
Over to you.
Thank you. All right, colleagues. So as you are aware of the title really is speaking to something that could be of interest to most of us, which is why we're here, I guess. Let me switch off my video, maybe to help some people that have got a bandwidth problem. So the idea here really is to talk about the foundations of statistics as they relate to data science. So if you think about data science, really, I could just draw 3 circles here and maybe call this maths and stats, and maybe call this computer science plus engineering, etc., right? So some form of computing. And of course, we could have the domain, which could be finance or agriculture, etc. I hope everyone can see my writing as I annotate. So data science is really then a combination of these 3. If you think about this as 1, 2, and 3. So, of course, one could define the combination of maths and computing as your regular machine learning, rather, applying mathematical and statistical techniques on a computer to learn some data distribution and things like that, for the computer to be able to perform some form of statistical or modeling or statistical inference. One could see that as machine learning. But the interesting thing with data science is the fact that data science becomes more applied than what machine learning typically does, you know. So this is why instead of maybe saying statistical foundations to machine learning, I mean, the title really has to speak to data science. So this is my definition that I'm adopting, or rather the definition I'm adopting for this particular school. The definition of data science is this type of definition. I hope we're clear with that. So this is just an overview of what the session is going to be all about. The theme of the session is really the role of statistics in data science, but of course we're going to get into some maths, etc., etc. So we want to explore how statistical reasoning provides the foundation for all data-driven decision making, and of course connect probability. We're going to define this very soon. Inference and learning from data in this case. As part of the unified framework for understanding uncertainty. I mean, statistics shines when it comes to quantifying uncertainty, and this is why I decided rather to call this statistical foundations to data science. And very soon we'll also be talking about why statistical thinking ensures some of the things that are becoming very important in the advent of artificial intelligence. I mean, we're talking now about trustworthy systems and interpretability and issues like that. So statistics really comes to the fore there and shines very well. Okay, so again, we're just extending here for everyone to know why we're here today and the next couple of weeks. Statistics matters in data science. You know, it really gives you the mathematical language to reason about uncertainty and variability and evidence. We'll talk about prediction, the difference between prediction and inference and things like that. Very soon we'll be getting into that. So one could actually think about data science as an evolution of statistics, perhaps not as a replacement of statistics, but more of an evolution. Like some people would say, statistics, data science is statistics on steroids, etc. But again, the role of probability and inference, these are kind of statistical concepts. Of course, one can argue that probability is more a mathematical concept than statistical, but I mean, that's a story for another day. Of course, you're not talking about measure theory and things like that, which is not what we're focusing on in this particular session, or rather in this school. So probability allows us to quantify uncertainty, to put a measure to the degree of how uncertain we are or how certain we are about something. Probability gives that type of language. And that is very important, of course, in data and data science. Of course, inference, drawing from populations, some form of sample. Think about a population. I always draw this to my students. Think about a population as the entirety of some items or objects that you are interested in studying. And you go and take a sample. That sample is meant to be representative. Think about the population. In the population here, you have what we typically call parameters. This is more like very elementary statistics, but I'm just going to paint that picture so that everyone is with us as well. We've got things like what we call parameters, which are nothing but just numerical descriptors of some population aspect. You know, you're talking about the population average, for example, which could be defined by mu. And then we're saying if you go to the sample, you can actually calculate maybe what we would call X bar. And this we call a statistic, right? The point is, if we're taking a different sample, the statistic was not going to be the same. If this was sample 1, and maybe we have sample 2, X bar 2 and X bar 1 need not be the same because these are two different samples, even if it could be the same size. So of course, the idea is how do we generalize from a sample to the population? And that's what we call statistical inference. We will touch a bit on this a little later on. But at the end of the day, there's a unifying framework, which is defined by this equation we're getting there. So if you actually ignore this part there, and you talk about y is equal to fx, this is really a mathematical equation, right? This is math. But the moment you come here and you say y is equal to fx plus e representing some form of randomness, then we are now dealing with stats. This is more of a joke, but the difference between maths and stats is actually just that epsilon there. So stats really worries about understanding the randomness that is involved in the data generating process and things like that. But the mathematician is really focused on, the deterministic. We would call that a deterministic. Sort of moving a bit fast because we want to cover a bit of ground. And some of these things I think are a bit introductory and elementary. So I'm not going to spend much time on the introductory stuff. Evolution towards statistical learning. There's been a lot of development in the statistical field, actually. All the way from John Tukey and all that, they emphasize the need for data-driven statistical analysis and all that. But now with the advent of the computer, machine learning also kind of Bayesian there. Now the combination of, or rather the statistician's approach to machine learning is what can be defined as statistical learning, which is really a good combination, rather a sweet spot between stats and computing. Okay, but the idea again is data science data science, something is moving in the wrong direction. Sorry for that. Modern data science extends, what classical statistics would do. I don't know if there's someone moving my slides because they're moving on their own. Okay. So classical statistics rather emphasizes on your regular parameter estimation and hypothesis testing, which is basically, if you think about it, small data. I'm putting in quotes because you might look for this term, you might not find it. This is just in opposition to what is typically called now big data. So statistical techniques were developed sometimes where experimental units were as few as 12, 20, etc. in the days of William Gosset, etc. All the statistical tests that were developed were based on data that was not that huge. But now the point is, if you think about data science, it's more like an extension to high dimensional data, and then there's need for regularization. We are going to touch on this as well when we talk about lasso and ridge regression, etc. I mean, all of a sudden, instead of having the regular data sets that you have where n is greater than p, in this case, n is really just the number of observations. If your number of observations is typically greater than the number of parameters you need to estimate, statistics shines there. Statistics is very good with this type of thing. Okay, but the moment you have this type of setup where the number, my slides are moving, I'm not sure, but don't worry, I'll just make sure that everything's fine. So if the number of observations is much less than the parameters, then there's a problem. Statistics can't handle this very well. And this is where now statisticians have also accepted that, the computer scientist is not really reinventing the wheel. They are rather contributing to the debate that has already been happening. Okay, so data science is more of a combination of the stats, the classical stats, and the data-driven big data approaches that the computing frameworks have produced. Okay. So statistical learning provides that type of framework where you balance the bias and the variance. We'll come to this. Very important. So the bias variance trade-off is a very important thing to understand when one wants to be a good data scientist. Okay. So at the end of the day, really, we want people to at least gain something from maybe doing better data science, right? So the continuum of learning from data, think about descriptive, inferential, predictive, prescriptive. I think there's more money as you go this way. Of course, that sounds like a joke, but the point is data science sit closer to decision making and decision makers, etc. And things become more prescriptive when you are making decisions. You want to know what should you do for something to improve. What should you, so you need a prescription. But the moment you are dealing with descriptive stuff here, over there, this is very elementary, as it were, describing what has happened. And of course, this is more your descriptive stats, etc. The moment you go towards this way here, you are becoming more should I say, applied, as in the sense of you are providing some solutions for decision makers, etc., etc. And that becomes very important. And by the way, I'm teaching at the business school, and this type of stuff becomes very important for managers, etc. But we'll focus on what we need to focus on today. Okay, so trustworthy AI. Someone will be wondering, why are we talking about AI when we're talking about data science? I think at the end of the day, everything is becoming automated, right? So the point is, once you automate decisions from statistical systems and data science systems, is it trustworthy? Yes or no? And this is where statistical reasoning actually shines as well. Without statistical reasoning, models cannot be accurate. Sorry, they can be accurate, but maybe not reliable. So accuracy is not everything. That's what statistics really claims. The point is you can have a very accurate model in predicting the price of cars in South Africa based on the price of eggs in New York. You know, that can be a very good model in terms of accuracy. But the point is that model reliable? Could be just some spurious type of relationship that you found there. So statistical thinking enforces transparency. If you apply for a loan at a bank and then they reject you and then they tell you that the system rejected you, you would want to know, why did the system reject me? And statistical thinking comes to the fore there. And this is the purpose and the theme behind the mini school. Rather, we want you to have an idea and appreciation of the contribution of statistics in data science. So this is the big picture. It's just not about numbers. It is really about responsible decision making. Of course, in the face of uncertainty. Okay, so here's a summary and the logic of the mini school. We're going to divide this into three. Today, we're going to focus on why statistics matters, developing the mindset of uncertainty and curiosity, based on the contribution of statistics to data science. And in fact, I wanted to do all this today, but I think I was a bit too ambitious. We will see how far we go today. If time permits, we'll probably get into some of the math behind probability and inference. And this becomes very important, of course, in data science. A data scientist should probably not be afraid of seeing a mathematical equation. And I think this is the purpose of session number 2, session B. That was a bit of a joke, but maybe not too funny. If you want to be a good data scientist, you should not be afraid of seeing a math equation. And I think the purpose of this session is really that. So then the later part here, we are going to focus on statistical learning, learning from data. We're going to get into things like the bias variance trade-off and things like that, and also talking about cross-validation. All those foundational concepts, they really come from statistics, but they are used a lot in data science, and one needs to have a good appreciation. That's my contention, or rather my argument. So 60 minutes for the first session, second session, etc. By the end of this session, or the end of this mini school, participants should be able to explain how statistics transform data into structured evidence, etc., distinguish between descriptive, predictive, recognize the philosophical link between uncertainty evidence and knowledge. Okay, then session 2, we'll get into the math, probability, as a measure of uncertainty, expectations, and, to quantify random behavior. Of course, we'll talk about other performance metrics with regards to data science and statistical models, etc. Then the last one really gets into more interesting things as well, with regards to overfitting and issues to do with generalization, etc., etc. Okay. We also want you to have a good appreciation of the connection between classical reasoning and predictive modeling. I think this is rather something that is developed. Predictive modeling has kind of developed from the classical statistical reasoning that we have always had. And that appreciation is important. It's more like, we're trying to just say if someone has learned data science and maybe they didn't do some good statistical module, whatever, we're just trying to say, okay, this is your grandfather type of thing. Well, this is a joke, but I hope you got the joke. So statistics can be seen as the grandfather to data science, right? appreciating uncertainty, etc. I mean, it's part of the learning objectives. So these are pedagogical approach that I'm going to use. We have a concept, and then we have some kind of equation that illustrates what the concept is really all about. So please don't be afraid of the math. We will definitely show some math today still, and then the focus will be on the intuition as well. What is the intuition behind the whole mathematical formula, etc., etc.? And of course, we have some form of example. But I must assure you that the examples that I'm going to illustrate here is not more like a coding example where I say, open your computer and let's do this, etc., etc. I think we can have space for that maybe at a later stage. I mean, for 3 hours, statistical foundations, data science, we might not have enough time for code. But yeah, I think we'll come to that at some stage. So this is the central equation behind the mini school. And if you can get an appreciation of what this is all about and what F is all about and what Y is all about and what X is all about, particularly with regards to modeling, etc., I would have achieved a lot, honestly. So, I mean, the point is any machine learning model that you can think of kind of revolves around this central equation here, where there's something that someone is trying to predict based on some input, and then they recognize that there's some randomness that is inherent in that type of system. And that is what that epsilon is showing us. And of course, X is showing us the input. F is some kind of function that you must learn from the data. And this is where the idea of machine learning comes in. Okay. So the challenge of data science, of course, is to separate these two responsibly. Which two? The deterministic part, which is the structure, typically something that could be some form of trend or pattern, but then the randomness is inherent there. And how do you separate these two? How do you minimize, the sum of squared errors? We'll talk about that very soon. So some key takeaways from this mini school, of course, is really just to understand that statistics provides some language of uncertainty, probability, inference, and inference form the core of all data-driven learning. Modern machine learning scales the same statistical logic. It's more like scaling, now doing statistics on a computer. I've argued that machine learning is doing statistics on a computer. So I think we've got a picture of where we're going. Okay, here's some references. That book is actually freely available. This as well you can find, if you search well, you can find it free on the internet. And this also is available free. So the books we are referring to here are really not something that you need to buy. So let me unshare, or rather, let me switch to today's session, which is this one here. Okay, give me a second, please. Let's just do the full screen one more time. Okay, so what is statistics? So these are the objectives of this session. We'll talk about some of the things we've already mentioned already, but I just wanted to start here so that we all start together. I know there's people who are going to feel maybe we should have started on deeper things, but I think this is important for everybody. So the core motivation really here is the fact that there's massive data sets, advanced algorithms, but then the point is uncertainty is not eliminated by how big the data is. In fact, the bigger data you have, the more advanced the algorithms become, the more is the need for transparency and interpreting how wrong the model could be. Think about a model such as ChatGPT. There's interesting research now where people start to ask, does ChatGPT know when it doesn't know? Okay, I don't know if you've got that. Should I repeat that? Does ChatGPT know when ChatGPT does not know? I mean, that's the idea of uncertainty. And in this case, we're saying maybe not. In fact, when I asked that question, I think some people were asking, do we humans know when we don't know? I think it would be too much to expect a computer to know when it doesn't know, when most of us, myself included, I think we tend to not know when we don't know, right? So we would be confident in our ignorance. And the point is, statistics really comes to the fore there to say, how can we quantify uncertainty in the example that I used, for example. Another interesting project, by the way, the idea of uncertainty in LLMs, etc. So every data set is really an imperfect snapshot of what reality actually presents. It is incomplete, it is noisy and often biased. Now the point is, with all these problems, missing values, measurement errors, sampling bias, and all that, we have more problems than those. I mean, we also can talk about the fact that correlation, like the example I gave of price of eggs in New York and the price of cars in South Africa, if they're correlated, it doesn't mean that one is causing another. Neither can you argue that sharks cause ice cream sales. Okay? This is a joke, but I think my jokes are not that funny. The point is, sharks are swimming because of the sun. And people are buying ice cream because of the sun. So there is a confounding variable that you might miss when you equate correlation to causation. And statistical thinking comes in there, and we're saying we need to see that patterns don't mean that something is causing another. Okay. For example, understanding my jokes here does not mean that you're understanding what I'm saying, right? Of course, that could also be a joke. Data does not mean better conclusions. I think we've had this misunderstanding, particularly now with a lot of data that has been observed. I mean, there's a lot of data that people are observing on a daily basis, hourly, data, particularly in fields like finance and all that, there's just a lot of transactions and things like that. It does not mean better conclusions when you have big data. In fact, it can amplify noise if that data is not analyzed carefully. Okay. So statistics provides conceptual and mathematical tools to separate the signal from the noise. Again, you can see the main thing we're talking about is that same main equation we talked about earlier on. So in essence, you can see statistics as the science of learning from data. The science of learning from data. Okay, think about that. Okay. So particularly now in the era of AI, machine learning algorithms often rely on statistical principles, and predictions are really probabilistic statements. There's some kind of level of certainty that you attach predictions to. Statistical reasoning allows us to quantify confidence. I think I've been talking about this all over and over, but we want to make sure that we all get the point. Okay, so there's a good example there where we're saying if you have two predictive models that give different outputs, without statistical inference, we cannot tell whether the difference is due to real performance variation or just chance. So statistics provides the evidence base for deciding which patterns, which models or relationships are meaningful. Statistics comes there. Okay, 3 pillars of statistics: description, inference, decision making. Again, you can take this from what I was talking about earlier. Sample, generalization, that's your inference from the sample to the population. But then after you've generalized from the sample to the population, you want to make a decision about the population. The decision is really about the population. And now here's a conceptual flow. Data, you summarize the data. This can be in terms of tables. This can be in terms of pictures, histograms, this and this and that and the other. What you're dealing with here is rather descriptive statistics. The moment you go like that, it's inferential. But inferential statistics is not everything. At the end of the day, you want to come to the, I would have said dollar, but rands in this case, right? You want to come to the decision. The decision has got to do with either it's a business decision that must be made or a health decision that must be made, etc., etc. Okay. So I'm sure we got the picture already. What is descriptive? What is inferential? I won't waste your time there. There's no generalization with descriptive statistics, but with inferential statistics, the idea is really to generalize to the wider population, generalize findings to the wider population. And you can talk about what we typically call confidence intervals, or you can talk about what we call hypothesis testing. These are both instruments for inference. Okay. All right. So you could widen this if you like. Instead of just saying collect data, summarize, you could now talk about a model in between here. Okay, so you can actually, this is now data science, right? We're saying there's a model that you're fitting in between here. And that model is meant to represent the data generating process. I guess that's why it's called data science, because you're trying to understand where did this data came from? Okay, what process led to this data? Okay, so it's a science of understanding where the data could have come from. And I think this is what the point is. If you can get that point, then you can understand where statistics comes in. Because the model we're talking about there is actually a statistical model. It's a statistical model about the data. And I've argued before that statistics is the science in data science, but I mean, that's not the argument for today. So where does statistics fit in? Even the collection of the data, description here, the summarization, inferential tools, quantifying uncertainty, validation, etc., etc. Okay. As the language of uncertainty, I think we've been preaching this story for a while now. Let's move. So the bridge between data and decisions, again, this is a very difficult bridge to cross if you don't have statistics. You might rely on intuition and things like that. Think about estimating click rates, testing some advertising designs and forecasting sales. All these type of things, all these type of problems rely on statistical inference. Okay, so you want to learn what has happened in the past, for example, for you to be able to make a focus. Demand forecasting, issues like that, macroeconomic interest rate forecasting, and things like that. They're all kind of dependent on statistical approaches. Even your regular neural network type of approaches, which is really computationally intensive, they kind of rely as well on statistical validation. We'll come to this very soon when we talk about cross-validation and things like that. Okay, good. I think we're moving at a very good speed, and I'm impressed. So the modern statistical thinking is not just about formulas. It's rather a framework for reasoning. It's a framework for reasoning in the face of data, in the face of reasoning about data in the face of uncertainty. So it connects data, models, and decisions through a framework of uncertainty. And of course, it also teaches humility, because the point is there's always something that you are not fully aware of, which is the error. The mathematician kind of fathoms the deterministic part. Again, that central equation is coming back. I'm sure you can see why this is a central equation in this class. We're saying this part here is deterministic, but this part here can humble you, right? That was a joke, but people are not laughing at my jokes. I'm not sure. Maybe I must improve my jokes next week. As George Box famously said, all models are wrong, but some are useful. Okay, I'm sure you can then get an appreciation of where statistics is coming here. It helps us measure how wrong the model is. Okay, so let us have an idea of how wrong the model is. Okay, again, we're still just talking about why do we need statistics. In the age of big data, we still need statistics to reason about uncertainty. We are repeating the same thing. Statistics transform data into raw insights. That's the final thought. Okay, so let's talk about the transition from data to knowledge. So if you think about data, we're saying you need to appreciate the fact that there's some form of uncertainty that lies around your data, around the data generating process and things like that. And statistics comes there as a procedure. If you think about the procedure of going from data and uncertainty to knowledge and decisions. Of course, this knowledge and decisions, they're going to be done with the understanding that what we have from the data is probably not ground truth, as it were. You don't have all the information in the world. I remember one of the mathematicians, Ivan John Good, was talking about causality. In fact, I studied this when I was still a student. And you talk about defining probability raising as some form of causality. But then the assumption would be that you should have all the information in the world. And I mean, the statistical footing does not take that type of assumption. I mean, we do know that we don't have all the information in the world, and of course, uncertainty is always present. That's what we're trying to get to here. The model is a model. It's just a simplification of reality. Structured process, of course, now to quantify how much confidence can we put in the data that we have, and that's where the idea of confidence intervals, etc., comes in. Okay, so we've talked about this already, but these are just good examples in terms of where probability comes in, where descriptive statistics comes in, where inference comes in. So I'm going to share this slide as well, so people can just go through this. Let's get into an example of descriptive statistics there. Very simple example. The idea is you can calculate the sample mean. That's probably one of our first equations, right? Very simplistic. Sample mean. In this case, you're just adding the values and you divide by the total number of values. Very easy stuff. But the point is, there's something that this can reveal. Just this simple calculation can reveal something about the structure of your signal and things like that. Of course, you don't want to stop here. I mean, this will be a very early stop if you stop here. You want to go beyond this. And this is where probability starts coming in. So how likely are things to happen and things like that? We define probability. Why? Because the bridge between samples and the population is rather from the sample to the population. We're going to talk about what we call sampling distributions. Sampling distributions. So sampling distributions is that rather the idea of saying, if you take a sample and you calculate X bar, and you take another sample, you calculate X bar 2, X bar 1, X bar 2, X bar 3, another sample, X bar 4. The point is, these sample statistics, which is rather your sample means, these values here that we're calculating the means, they're going to be different. And if they're going to be different, what can you say about the population, parameter, which is in this case mu, the population average? So this is where probability comes in, because we're saying for you to make a generalization from the sample to the population, there's going to be need to find what is the distribution of the sample statistic. And that distribution, we call it the sampling distribution. And once we're talking about a distribution, probability has to be defined. And this is why I'm defining probability here. So probability is just a measure of uncertainty, a value between 0 and 1. You can have axioms of probability, etc., etc. We're not going to focus on that. But in a classical definition of probability, you can define probability as the number of possible or favorable outcomes over total number of outcomes. Think about tossing a coin, and what is the chance that it will land on a head versus the chance that it will land on a tail. If it's a fair coin, it will be 50-50 type of thing, right? And why do we need to ask such questions? Because such questions will help us to understand the relationship between what we got from the sample and what we can expect in the population. I'm sure you can see the importance of probability. Okay. So what is the likelihood that a customer changes next month? This is an example of what a probability question could be that one wants to answer. The probability of observing some extreme weather. This is a very important question for an insurance company, right? Probability of someone's death is also an important question for an insurance company. Of course, the point is, once we bring it to our models and we say, how confident can we be about the model's predictions? It becomes even more important for us. from a modeling point of view. So every machine learning algorithm implicitly defines probability, or rather a probability model. They kind of rely on probabilistic error terms, even in sophisticated machine learning models. Okay, generalizing from samples to population. This is exactly what I was talking about earlier. So estimation of parameters, confidence intervals, hypothesis testing. You could talk about estimation as point estimation versus confidence intervals, etc. But at the end of the day, we want to do some kind of generalization from the sample to the population. I hope this picture is sticking in your brain, because this is the foundational picture of what statistics is really all about, from samples to the population. Okay, so mathematically, think about theta being some form of parameter there, and we're saying the estimate of that parameter is really a function of the data. It's a function of the data. So if you have good data that represents, by good what we mean, data that is representative of what is happening in the population, you can have a better estimate of the parameter, which is now theta hat. That little hat means you are estimating that parameter. So if you think about minimizing the distance between the estimate of the parameter and the true value, this is what a good model does. Okay, you want to minimize that. You want to minimize the distance between some ground value, which we are assuming to be there. Of course, this is now classical statistics. I'll get back to this very soon. So with classical statistics, we assume that there is a value somewhere, of a parameter that we are looking for. But then we assume that that value is fixed. And then we use some data to estimate that value. Okay, so in a different world, which we would call the Bayesian world, things operate a little different, but I don't want to talk much about that for now. We'll come back to that. Okay, so from raw data, you really want to go to knowledge via information, but to wisdom. If you think about it, of course, it's very unlike science for us to talk about wisdom, right? But that's where we want to go. Okay, so examples in practice where we go from data to decisions. At least people are understanding my jokes, and I like that. Predictive modeling for loan approvals. This is a very important problem for banks. I used to work in credit risk very briefly, but a very important problem. Quantifying the probability of default based on past defaults and past information and things like that. And of course, people are getting lots of money from that, right? Okay. Descriptive statistics, we've talked about that. Pillars, okay, let's move a bit. Let's come here. The difference between descriptive statistics and inferential statistics. Here we're focusing on the sample, here we're focusing on the population. You can see here we're calculating things with regards to the small n. But then the point is that small n is the population size. If you wanted to define x, sorry, rather not x, but mu, this would be 1 over capital N, summation of I is equal to 1 up to capital N, xi. What do we mean by this? This would be the population, mean. Okay, the population mean is based on the population size. But this is not realistic, because we typically don't have the whole population, unless if it's a very a small experiment we're dealing with. But typically, you're talking about big populations, etc. And this is why we go for the sample, because it's rather expensive and inaccessible to get the whole population, etc. A few examples there which you can read, I think, at your own leisure. Let me move a bit. Again, zooming in versus zooming out. I mean, the sample is really focusing here. Descriptive statistics is focusing on the sample, whereas descriptive statistics goes out to the population. I'm sure you can see the picture is coming back. Descriptive statistics require data, but inferential statistics require data and probability theory. Okay, we're going to use probability. We'll be using probability theory, which is why you will see that there's going to be a focused section on probability and distributions and things like that. Here's a good example of, you know, a scientist here, in this case, who wants to test whether a new marketing strategy significantly increases sales. I mean, this is an important problem. You don't want to just increase, you don't want to just adopt a new marketing strategy and not test whether that marketing strategy has improved your sales or not, and things like that. So it can be tested using hypothesis testing. Very key to data science. A very simplistic approach, but very key to understanding certain things, with regards to application of data. Again, we can talk about some connection from from statistics to machine learning. What we typically call descriptive statistics in machine learning or data science, you typically call that exploratory data analysis, EDA. And what we call statistical inference or inferential statistics in data science and machine learning, you typically call that model validation and things like that. So these are just rather new terms for things that have been existing, right? Organizing and summarizing data, etc., etc. We're looking at the data. That's what descriptive statistics is really all about. We're looking at the data, and then inferential statistics goes beyond what we're looking at to maybe what we can't see. We want to look at the unseen, right? I think that's what inferential statistics tries to do. So the statistical mindset really is thinking that goes beyond computation. In fact, one of the statisticians who was like the president of the American Association, etc., apparently said that there was coming a day where statistical thinking will be as necessary for efficient citizenship as the ability to read and write. I hope you got that. I think this is the day where we're living now, where statistical thinking is necessary for efficient citizenship as the ability to read and write. Okay. So we want to shift our mindset from us looking for the true value of something and rather thinking about the distribution probabilistically, and that's statistical thinking. Variation is everywhere. And we all appreciate this. And this is where the epsilon is coming in. There's variation in heights. There's variation in people understanding Farai's jokes. Yeah. There's variation in temperature. There's variation in customer behaviors. There's variation in everything, right? And statistics really comes there by thinking of this variation in terms of distributions, okay? In terms of distribution. So it's not one value we're looking for. We're saying, what is the distribution of this type of phenomena? For example, here is an example of what we'd call a normal distribution. Okay. So in data science, model parameters are not fixed. They actually have uncertainty. That's where the idea of a distribution comes in. Predictions are also probabilistic. So of course, there's going to be some conditional aspect we're going to bring there. Given the data, what is the prediction? Okay. Let's define a few things here in terms of statistical thinking. We'll talk about probability. Again, this is just what we would call conditional probability. So we're saying, given B has happened, what is the probability that A will also happen? Okay, so we define it that way. So if you think about that type of probability there, we're saying, instead of looking at the whole sample space, you want to, this sample space here, S, you want to limit the sample space, in this case, to B. If there's a B there, okay, something is jumping up and down. If there's a B there, event B, the probability that A happens after B has happened, we're saying it will be now that intersection there divided by the whole of B. I hope you can see that picture. So we're saying, instead of dealing with a full sample space, we're now going to limit our understanding to B, because B has already happened. So this is the idea of conditional probability. It becomes very important. Look at this example, for example. Maybe you want to measure the probability of A, in this case, happening, which is the probability that the email is spam, given that it mentions the word win something. So you can calculate that probability using this formula here that we just looked at. That's what the idea of conditional probability really does. And it's a very important concept because a lot of statistical modeling is based on conditional thinking and updating probabilities, revising probabilities in the face of new data, etc. So conditional probability um, really expresses how we reason about cause and context and evidence. So when new evidence comes in, you can update your beliefs. And this is the basis of the other side of life that I was talking about when I talked about classical statistics. The other side of life is what is called Bayesian inference or Bayesian thinking. And it's based on this type of formula here that we call conditional probability. But don't worry much about that for now. So conditional probability in everyday life, some examples. Probability that it rains given that it's cloudy. Probability that it rains given that it's cloudy. Probability that you become a good data scientist given you study or you worry about statistics. That's a joke, right? I think that probability is very high. I think that probability is very high. The probability of becoming a good data scientist, if you take say, statistics seriously, I think that probability is quite high. Probability that the disease is present given that there's a positive test. Probability that a customer changes given some low engagement. Things like that, okay? I think my screen is still sharing. Is that correct? Was that a bounce on my end? Looks like my screen bounced. Am I still sharing? Good. I think I am. Okay. So the statistical intuition um, of conditional probability is the fact that learning from data is really conditioning. We're saying we're assuming that this is the truth that exists. So what can we say about the data generating process? If the data is what we can see to be the truth, what can you say about the data generating process? But then if you have new data, you might need to update the model, etc. I'm sure you can see the idea why statistical thinking is important here. So the Bayesian mindset, same formula, but now we're just adding a few things here. So think about A as your prior belief. Think about A as your prior belief, which exists. The probability of it exists there. But we're saying you might want to talk about A given B, which is now your posterior. This is now the Bayesian world I was talking about. It's good that we are talking about it on the first day, so you can start thinking about it because it becomes very important later on. So you're going to have to update your beliefs given some new data. And in Bayesian, rather Bayesian reasoning is really a mathematical form of learning from experience. So Thomas Bayes actually did some wonderful work, which I think he was very modest not to publish. I think it was only published after his death. And it has become a cornerstone of statistical learning from experience, if you think about it. Okay, this mindset is very important in data science, of course, because of uncertainty. There's need to update our beliefs. We want to also think about the fact that this type of thinking is what underlies model evaluation, prediction intervals, and focusing and probabilistic deep learning. Deep learning becomes very interesting the moment you bring statistics and statistical thinking. It becomes very interesting, actually. Probabilistic deep learning. You talk about Bayesian neural networks and things like that. Okay. I see the time is clicking. Conceptual takeaways from the statistical mindset. We're saying statistics is really thinking in probabilities, not in absolute terms. It's all based on what we were talking about earlier. Okay, I don't know, Prof, if I should teach until 3 in this case, or do we need to give time for questions? I see it's almost 5:02. I don't want to steal people's time. Should I proceed, Prof? Okay. I think that's a green light, right? Okay. So there's need for a mindset shift from deterministic mindset to a statistical mindset, which accepts, the role of variability, and this is what we've been talking about. We've covered that. Again, just a few examples there. Height of adults in a class, in a population, there's variability, and you need to think about epsilon in this case as a measure of that variability. Conceptual differences between thinking in distributions and not thinking in points. We're just rehashing the same point. I'm sure you can see that. Again, now we are getting a bit deeper here in terms of perspectives. Maybe not deeper, but rather defining the perspectives. So there's a frequentist approach, which is the classical approach, which really assumes that the data or rather the parameter is fixed somewhere and you must look for it. But then the Bayesian says, no, it's not fixed. There's a distribution around that parameter. There's a distribution around the parameter, and we want to find that distribution. And once you have the distribution in the parameters, you have a distribution in the predictions and things like that. Okay, yes, the slides will be shared. I don't know, maybe I should stop very soon. Statistical thinking, we're coming back to that example of the spam based on, conditional probability. You can read this a little more later on with some interpretation there regarding statistical thinking. Okay, with an example now, we're coming back to that Bayesian mindset, now with a good example in terms of a medical taste. But I have a feeling that I should allow for questions. I don't know if I should stop now. Okay. I think I should pause for questions, right? But I don't know if Prof is there. Prof Francisco. Let me see. Okay. Okay, great. Oh, it's a webinar. It looks like we're in a webinar. So, well, colleagues, if I should maybe just give a picture of where we're going, because I think I might still have a minute or two. If I should give you a picture of where we're going, there would be a comparison between statistics and machine learning. We will talk about machine learning views and how do they compare to statistical views. We talk about statistical learning theory. This is all part of the first session, which I would love people to go through this. Once you get the slides, I'm going to share the slides with Prof and the team. Then if you can go through some of this before the next session, that would be beautiful. But I see Prof is ready to take over.
No, I didn't want to interrupt you. No, thank you very much, Farai. It was a fantastic first lecture in this new mini school that has almost 200 participants. That's really wonderful. And if you are happy to share the slides with me, we can upload on the NITheCS website so that everybody can download them and be ready for next time. Yeah.
Yes, I can do that, Prof.
And I see there are lots of smileys and hearts and thumbs up flowing up the screen. So well done, well done.
Thank you, Prof. Thank you.
And I think there is one attendee, Estibel, raising his or her hand. I'm not sure. And let me allow them to talk. There is also, Estibel, you're welcome to, and Jimo as well. You're welcome to ask your question. You just need to unmute yourself.
Yes, can you hear me?
Yes, we can hear you, Estibel.
Yeah, it's me, Estibel, from Benin, originally from
Okay,
Ethiopia.
wonderful.
Originally
You are joining us from far away. Yeah.
From Ethiopia.
Excellent.
I'm a little bit confused about Bayesian. and its difference with reinforcement learning. I don't know if we will cover in the future sessions, but if
Good
possible.
question. That's a good question. Let me try and tackle that in the future sessions. Yeah, it's not really foundational. It's a bit it's a bit, I could almost say, intermediate. But let me try and answer you in the next session. Yeah.
Okay. Thank you.
Thank you, Farai. Thank you for the question. And now Jimo has also a question.
All right. Thank you, sir. I don't know whether you can hear me, sir.
Yes, we can hear you clearly.
All right. Thank you, sir. I want to actually first thank you, sir, for this wonderful presentation, wonderful webinar. Actually, this really helped me so much in my research. Now, I just need a little guide from you concerning what I've listened to so far concerning my research. I'm trying to work on how I can use statistical model to predict the energy potential of some areas which have collected their wind speed. So now my problem now is I don't know the chronological, as in I don't know the strata I'm going to follow to where I'm going to get I've gotten the data already. Now I'm now looking at how I'm going to take to my decision level. So if you can just give me a kind of guide on what are the steps I can take after getting the data set, the wind speed data set.
Typically, Jimo, if you are doing research, you typically should have a methodology, right? So, yeah, I mean, so I think your methodology should kind of inform you, because you're not just getting the data from nowhere, right? I guess you had a research design, what they call a design, and there was a methodology that you were going to follow, depending on the kind of hypothesis you had. Of course, hypothesis being just some educated guess of what the truth could be in terms of the data and the data generating process, etc. So I think that's really a question of, do you have a methodology, and what type of methodology do you need for which type of data? I mean, if it's a prediction problem, like which is what I'm hearing here, you could use different regression type of techniques, right? Depending on the outcome, whether the outcome is numerical or categorical and things like that, that would inform which type of statistical technique or data science or machine learning technique you could possibly employ. But yeah, I think that sounds like a research a research question, which is beautiful. I mean, to have here. I wish I could spend a little more time, helping. But it sounds like you probably need to think about the methodology. Yeah. A methodology that can be used in the particular for the particular objectives that you have. Yeah, for your research. Yeah.
All right. Thank you, sir.
Thank you for your question, and thank you very much, Farai, for the answer. And I think this brings us to an end of this first lecture in the mini school. So Farai, thank you so much. There is still more clapping going on, and I'm sure that if there are further questions or comments, people will be able to ask you next week. Yeah.
Next week.
Thank you very much. Farai, thank you very much to all the participants. It was really nice to see that there is a market for this mini school. Yeah, that's excellent. And then we will see you again next week. Yeah.
Thank you.
So thank you very much. The slides. So I can see someone asked for the link. We put the slides on the NITheCS website. You will find them there next to the announcement of the event. Yeah. Thank you very much. Thank you.
Thank you, Prof.
Bye-bye. Have a good afternoon. Bye.
Bye.